I'll begin with a word of prayer. So, Heavenly Father, we thank you for this time we have to study your creation. Again, I thank you for these students. Just pray that you'd be with us today. Help us to glorify you in what we do, and just help us to understand a little bit more about this special relativity, Lord. In your name I pray, Lord Jesus. Amen. Okay, so, all right. Let me just take a second to talk about something more basic. This is an attendance sheet. The idea of an attendance sheet is for it to go to every student in the class. So when it gets to you, it is imperative that you find another student who has not already signed this and give it to them. We continue this process until everyone has gotten the sheet. Are we clear? Okay, good. See, because like last time, I don't know who the weakest link was, but I could look at these checks. I could figure out one of these 5 checks is the person that. What's that? Let's see here. What's that? I did start it in the back last time. I'm starting it up here this time. It's the back. Yeah, the front is saying the back is terrible. But all right. Did you add a day? Thank you. All right. Let me put this silliness away. So I talked about last time that the physics community came to an understanding in the 19th century that light was a wave, right? And then the question is, if it's a wave, like other waves wave in something, right? Like a wave on a string or a wave in water, there's some kind of medium that propagates the wave, right? So then the question is, what is light waving in? And the answer that they came to in the 19th century was something called ether, right? Thank you. And so then they proposed various experiments to try to figure out the nature of the ether, whether it was everywhere and the Earth just went through it and didn't drag it along, or did the Earth like drag this luminiferous ether along with it? There were different competing hypotheses. Various experiments were done. Ultimately, the most refined version of this experiment ultimately was the Michelson-Morley experiment, which in 1887 conclusively proved that it didn't seem like there was such a thing as ether. I mean, it just seemed like, yep.
What was the name of the experiment again?
Michelson-Morley. Yeah. So this is the famous null result. Essentially, it proved that the speed of light was the same whether we're on one side of the sun or the other. It didn't matter where the orbital motion was. If there is such a thing as ether, it doesn't seem like relative motion with respect to this ether has any effect whatsoever on the speed of light. So this is one thing that was there. And I think there's some debate, but the people pretty much believe this is not what motivated Einstein, actually. For Einstein, Einstein was engaged in various thought experiments as a teenager and things like this, and I think it was more the thought experiments which prompted him to discover special relativity, and also the fact that there's an impasse between classical electrodynamics, which is the theory of electricity and magnetism, and classical mechanics, in the sense that, and this is a slightly formal statement, but if you study Maxwell's equations, they don't naturally transform under the transformation equations of classical mechanics. Classical mechanics, the natural transformations are what are called rigid motions. Like we talked about this before a little bit, constant velocity motions, and you have a rotation, right? That's about it. But the thing about classical mechanics is altogether there's a universal notion of time, right? we just take this for granted. We talk about time. Do we have to talk about the time with respect to one coordinate system or with respect to another? No, we just talk about time. Universal, overarching, Newtonian time. This is implicit in everything we've done, right? But this is what has to be given up on in order to get that in order to have a constant speed of light. It turns out that you have to give up on this privileged and special role that time has in terms of like it being the same for all observers, that there's a universal timeline that we all share, all different inertial observers. That's just not the case if we believe special relativity is true. And there's a lot of experimental evidence to suggest that special relativity or something like it is true. So let me show you how Einstein explained his theory. All right? These were the two basic principles that underlie special relativity. Number one, the laws of physics are the same for all inertial observers. There's no preferred frame of reference. That's the first axiom. This actually, in some sense, was already present in Newtonian mechanics, but the difference is that we mean a different thing by inertial observers. But so this is actually very conservative. This is essentially already part of Newtonian mechanics, axiom 1. But axiom 2 is shocking. The speed of light in free space is the same value c according to all inertial observers. This is like a really bizarre thing to say in terms of what we know about relative motion, right? Because of course, if you throw a baseball in a train, right? And the train is going a certain speed, what's the speed of the baseball? Well, it's the speed of the train plus the speed of the baseball that you throw, right? So if light behaves the same way, how could it have the same speed with respect to all inertial observers? Because it seems like if you shine a flashlight on a train that's going fast, it ought to be going faster, right? That's your intuition from classical mechanics, because we have a basic idea, which is velocities add, right? We derive this. The velocity in a moving frame of reference is the velocity of the frame of reference plus the velocity, right? You work some problems about this. That has to somehow give way if this axiom 2 is true. So it's not immediately obvious, but this second axiom has shocking results. And let me derive them for you. Well, some of them. So what we're going to do right now is we're going to derive, I'm going to look at the derivation of what are known as Lorentz transformations. So the Lorentz transformation, it relates to frames of reference, to inertial observers. And so here's the situation. You've got one frame of reference like this, all right? And we'll call that the S frame. And then you've got a second frame of reference, we'll call it the S prime frame, like this. And I don't mean that I would just draw them exactly overlapped, but I want you to see the difference, okay? So we have X and the X prime. And so in the S frame, we measure, let's say, time and position. In the S prime frame, we measure, again, time and position, but this time T prime and X prime. All right? And so these are two different coordinate systems. They're going to describe, let me say more about these coordinate systems before I get further. We assume that they're lined up. We assume that they have coincident origins at time 0. So like at time 0, they overlap. And furthermore, we're going to assume that this one is going with velocity, let's say v, in the x direction. That's the other assumption. We're going to look at the case that one of the frames of reference is moving with constant speed in the x direction of the other, all right? So the prime frame is moving with velocity v in the unprimed frame. What's an event? So these are two descriptions of events I mean, an event, let me just get to the point here. An event is a time and a place. All right? That's what I mean by event. Event is a pair of time and space. And listen, really, of course, you're like, well, space is not one-dimensional. Space is three-dimensional, right? So yeah, there should also be x, y, z, and there should be a y prime and z prime as well, but we can just focus on just x prime and t, just for the sake of brevity here. All right? So here goes. To start with, we'll suppose that x prime is equal to ax plus bt. And we'll suppose that x, on the other hand, is equal to a prime x prime plus b prime t prime. All right? So that's our starting assumption. We'll assume that there's some kind of linear change in coordinates that you can make here. And this is not, well, I wouldn't say it's linear, but these could be functions. Like a and b could, maybe they're functions of, they're probably going to be functions of the velocity somehow or another, right? Okay, so then what? The question is, what are the a and the a prime and the b and the, what are these constants? So we'll start by studying the origin. So you study, excuse me, x prime equals to 0 with respect to s. Goodness gracious. So you have the equation 0 is equal to ax plus bt. All right? 0 is equal to ax plus bt. What does that say? Well, that says that if we differentiate that with respect to time, this says that, a times dx dt plus b is equal to 0. So what this tells me is that v, which is equal to dx dt, is in fact minus b over a. So v is the velocity of the primed origin with respect to the unprimed frame. So it makes sense what we just did. There's its velocity. So apparently the velocity has to be related to the coefficients like this. All right? And likewise, if we look at, since, s prime has velocity minus v in my bad. Sorry, I lost my place here. I'm dummy. So let's do the same thing with respect to x equal to 0, all right? If we look at x equals to 0, what's that give us? That gives us 0 is equal to a prime x plus a prime x prime plus b prime t prime, right? So this would be the equation of motion of the origin of the s frame in the s prime frame. If I differentiate this with respect to t prime, what does this tell me? I get a prime dx prime dt prime plus b prime equal to 0. So therefore dx prime dt prime is equal to minus b prime over a prime. Yeah. No, these are just labels. Okay. Yeah. The primes are all labels. And that's true throughout relativity. If you see prime, it's a label. We use a prime for the label of the other coordinate system. Otherwise, there would be this horrible proliferation of ones and twos, So, okay, but then there's a fundamental principle here, which is that, think about this. If you've got two coordinate systems that are lined up, right? If the prime system is going with velocity v with respect to my fixed coordinate system, what is my velocity with respect to the primed coordinate system? What happens to me is that the prime system goes away from me. I have velocity minus v, right? So this is called v reversal symmetry, and so this still must be true for relativity, because this all has to reduce to Newtonian case at like low velocity, so this has to be equal to minus v by that v reversal symmetry I just talked about. So what does this tell us? We have some relations. We've got what? We've got b is equal to what? AV minus AV, right? And we've also got b prime is equal to what? A prime v. So we can plug those into this. What happens to them then? What do we get if we plug those in? We get x prime is equal to ax. I'll eliminate the b's. All right. So minus av. I'm bad. Av what? Avt. And I also have x. Sorry, I've lost. Yeah. So I also have x equals to what? A prime, x prime. What's b prime? B prime is plus a prime vt, right? So we can clean these up a little bit. We actually have what? X prime is a times x minus vt. And x is equal to a prime times x prime plus vt prime. All right. So then what? What's part of the axiom 1? There is no preferred frame of reference, right? So think about this. A is to S as A prime is to S prime. They play exactly the same role. If there was a distinction between these values, there'd be a preferred frame. Therefore, A is equal to A prime. All right, so we've got x prime is a times x minus vt, and x is equal to a times x prime plus vt prime. We still haven't used that the speed of light is constant, right? So far, everything we've done has just been based on like either the reversal or that. Okay, so next up, we want to look at a light in both frames of reference. So consider a light ray, if you like. And I'll use the notation in my notes. So let's see here. So I said let phi of t be positioned in the tx frame. And we'll let psi of t prime be the position of the light in the primed frame. All right. So what is the relation between these? What is the relation between these position functions, right? These are general relations that hold for all trajectories, right? So in particular, they have to hold for the trajectories of light. So that relates this phi and the psi in the following way. Basically, I'm just saying set this equal to x and set this equal to x prime. Okay, that's all I'm saying. So what that means is we have, for example, psi of t prime equals to a times phi of t minus v times t, right? And we also have vice versa. We have that phi of t is equal to a times psi of t prime plus v of t prime. So this is the relation between how we describe light in the prime and the unprime frame. And now you guys tell me, what would d psi dt prime be equal to? This is the velocity of the position of a light ray. What's its velocity equal to? This is not up for grabs, right? Like this is by definition equal to c, right? So that's equal to c. You guys got me? Okay, cool. So that's equal to c, but what else is it? Well, it's the time derivative, right? So this a has to be a constant with respect to t, ddt of, well, ddt prime, right? Of phi of t minus vt. How do you differentiate? How do you differentiate if you are differentiating with respect to t prime and you've got a function of t? How does that go? What's the rule? You have to do the chain rule, right? So chain rule gives me a d phi dt, and then we've got a dt prime, chain rule, and then minus v dt prime. Let me put it together here. So that gives us c is a times, and what is d phi dt? C, right? Because the speed of light in the prime frame is c. The speed of light in the unprime frame also c. So we have a times c minus v times dt prime. But we can just as well calculate the other way, right? So likewise, c is equal to d phi dt, right? Which is going to be a times, notice the plus instead of the minus, so we get a times c plus v, and this time the chain rule will pop out not dt prime, but dt prime dt. Switching the roles of prime and unprime, same calculation. Now, so you take these two equations, right? We call this 1, we call this 2. And what we do is you multiply the equations. So what do you get? So we get c squared is equal to a squared times c minus v times c plus v, and then times dt prime dt. Well, that's convenient, because then the dt primes cancel and the dt's cancel, right? And you're just left with what? You're left with the equation c squared is equal to a squared times c squared minus v squared. V is the given velocity of the prime frame and the unprime frame. A is the thing we're trying to understand, right? Now we understand it. What's its value? Apparently, A is equal to, c over the square root of c squared minus v squared. And we can take A to be positive without loss of generality. And then if you do the algebra here, we can rewrite this, right? So A is actually equal to 1 over the square root of 1 minus v over c quantity squared. So here's some standard notation. We let, so this is definition, beta is v over c. So, and gamma is equal to 1 over the square root of 1 minus beta squared. So explicitly, gamma is equal to 1 over the square root of 1 minus v squared over c squared. A lot of times, the way that special relativity appears is it basically amounts to multiplying something you already know by gamma. Think about this gamma function. How does it work? So gamma, you could either think about gamma as a function of v or as a function of c. If we think about it as a function of v, so let me think about it as a function of v, right? What is gamma of 0? Plug in 0, what do you get? You get 1 over the square root of 1 minus 0, also known as 1, right? What's gamma of c? Ooh, that's a problem, isn't it? You got division by 0 if you try this, right? Which means don't do it. So this does not exist. In fact, the domain of gamma is minus c to c, c not included. So the allowed velocities for special relativity are just minus c to c, right? The magnitude of the velocity cannot exceed c for this mathematics to be, well, real. Okay, so now that we know all this, we can come back and let's put it together. What do we got? We've got, let me go back to the very start and just clean it up, write these equations down for us for our future reference. Listen, I could just write the equations down that I'm showing you right now, but I wanted you to see that we can derive these equations I'm writing with some relatively simple arguments if we just have a little bit of time, right? They're not that difficult to derive. Let's see here. So what we have found is that x prime is equal to gamma times x minus vt. And on the flip side, we've got that x is equal to gamma times x prime plus v t prime. Now, can you guys help me out? How do we solve for t prime in this? Because I'd like to figure out what t prime is. Can you help me solve these for t prime? How would we do it? Let's see here. This would, I get what? Gamma vt prime equals to what? X minus gamma x prime, right? You guys with me so far? And then what was x prime equal to? X prime is equal to, well, x prime is equal to, so I get a gamma squared x minus vt. I hope this doesn't all work out to 0. That would be annoying. So apparently t prime is equal to what? X minus gamma squared times x minus vt, all divided by gamma v. Well, that's a mess. Man, I sure hope this works out. It'd be so embarrassing if this didn't work out. You guys are good at algebra. Help me out. How about we, let's put all our x's together, right? What do we got here? We've got x times what? What's the x? X has got what? It's got 1 minus gamma squared, right? Divided by gamma v, right? That's the, so you've got, these are all your x's, right? How about the t term? What you got on t? On t, you've got yourself a, what? Plus t times what? Gamma squared over gamma v, right? Do these simplify? I sure hope these simplify. If these are the equations, it's really not that pretty, is it? Anybody? You're like, well, gamma squared over gamma v, that's definitely what? That's definitely what says here. We got t prime. I guess I should figure it out. 1 minus gamma squared over gamma v. How's that go? What is 1 minus gamma squared? So you got 1 minus 1 over 1 minus v squared over c squared, right? Divided by, oh, my bad. What am I doing? Sorry, that's a bad path. Let me be lazier. So you got 1 over gamma v minus, I think, gamma over v, yeah? Let me factor out a gamma from that and see what happens. Maybe something good will happen. I don't know. If I factor gamma out of that, I would have what? I would have 1 minus gamma squared over v gamma squared. What is 1 minus gamma squared? Let me work that out. 1 minus gamma squared is 1 minus 1 over 1 minus beta squared, which is 1 minus beta squared minus 1 over 1 minus beta squared, which is beta squared over beta squared minus 1. Maybe that's helpful. I should just use that. This is probably in my notes that I'm not looking at. Yeah.
What happened to the velocity in the numerator?
Where?
On the, you got the t prime equals, and then there's that's multiplying the t.
This one, which here?
No, down. You're looking up. The numerator and the velocity.
Are we talking about this one?
Maybe.
Oh, thank you. Yeah, they cancel, don't they? Where were you 5 minutes ago? Come on, man. Throw me. Help me. I asked for your help. Thank you. I mean, better late than never. Thank you. I knew there's something wrong here. That makes much more sense. That's a gamma. How does this simplify? I just worked out 1 minus gamma squared is beta squared over beta squared minus 1, right? And then I'm multiplying that by 1 over v times the square root, excuse me, 1 over, good grief. Multiplying that by v by the square root of 1 minus beta squared, yeah? That's what gamma is. 1 over gamma is that. There's a simplification here, right? So what we're looking at then is v squared over c squared divided by v. And this gives me a net total of 1 over the square root of 1 minus beta squared, right? Which is also known as gamma. So what we have here is v squared gamma divided by c squared. But not a v squared because the v canceled, right? So I got a v gamma over c squared. All right, finally. Good grief. That should not have been hard. So T prime apparently is just equal to gamma times T, assuming I haven't made a stupid sign mistake here, V x over c squared. There we go. Let me record them over here for posterity. So these are the Lorentz transformations. X prime is gamma times x minus vt, and t prime is equal to gamma times t plus vx over c squared. These right here are the Lorentz transformations. Now, Lorentz suggested these transformations before special relativity was invented, discovered, however you want to look at it, by Einstein. Lorentz proposed that these transformations could be used to explain like the null results in the interferometry I talked about last time. So this is just like an ad hoc, well, maybe the motion, because of the motion, there's like this compression or apparent compression according to these rules. He didn't derive them from basic principles like we just did, as far as I know. But anyway, these are the Lorentz transformations. Okay, so now we can do things. For example, we can let me see how much. Once you guys start whispering to each other, it makes me nervous. Let's see here. Hey, stop that. So there's a couple different paths we can go down here at this point, right? Let's see here. So example 1. Suppose we place a clock at, let's say, x equals to 0 at, t equals to t1, right? So we'll say x1 equal to 0. Then the clock ticks. And it's still where it is at x2 equals to 0 and t equals to t2. So how much time has passed for the clock in the S frame of reference? So what's the delta t would just be what? T2 minus T1, right? Goodness gracious. What's wrong with me? T2 minus T1. This is, duration of time in S frame. How much time passed between these events in the moving frame? So what is delta t prime, right? So we could say t2 prime, right, minus t1 prime. How do we figure out the time for event 1 and event 2 in the prime frame? So I'm saying that this is event 1. This is event 2. All right. So we use the Lorentz transformations, right? And I'm assuming that the frames are situated like we've been talking about today, all right? The prime frame is moving with velocity v with respect to the unprime frame. And so what we get then, right, using this equation I fought hard to get, is gamma times t2, right, plus v times what? 0 over c squared. There's your t2 prime. and minus gamma times t1 plus v times 0 over c squared, right? Notice that putting the clock at 0 is immaterial, right? I could just as well have put the clock at a fixed coordinate in the S1 frame. What would have happened in this calculation? If I put the clock instead of at 0, hypothetically, suppose I put the clock at like 7. What would have happened? I would have put a 7 here and a 7 here. They would have just canceled. See that? It doesn't matter that the clock is at 0. That's not the point here. The point is that you get gamma times t2 minus t1. In other words, you get gamma times delta t. This is known as time dilation. So the time in the moving frame of reference is equal to gamma times the time in the stationary frame. Or we could look at it the other way, right? The time that you elapse in the stationary frame is the time you elapse in the moving frame divided by gamma, right? All right. Let's see here. What else can I tell you? Another thing we could look at, example 2. We could look at 2 events. Let's see here. So example 2. Let's see here. Let's try to do. I want to try to show you guys length contraction. So let's see here. Let's suppose we have a. I want to think about in the prime frame. You know, we have rod length, let's say L, right? So if you allow me to draw a picture here, well, not really a picture here. So here's the picture. So here's how do you measure the rod length L? So let's suppose that you have x prime equal to 0 and you have x prime equals to L, right? That's your rod. For the convenience of discussion, I'm just putting one of the ends of the rod at the origin of the moving system, okay? And how are we going to measure the length of a rod in the moving system? I'm assuming the rod is not moving either, right? It's just sitting there. We're measuring its length. So we can measure the length at the same time. So basically, I have 0. And we can measure it at time 0. We can measure it at time t prime. Whatever. I'm just measuring it at time 0 to keep things simple. And here I have L0. Oh, my bad. We put time first. So 0L. So these are events described in the t prime x prime frame. How do I find the corresponding length of L in the unprimed frame? What would that be equal to? So let me call this one. This is x1 prime. This is x2 prime, right? So notice that we have x2 prime minus x1 prime. That's my delta x prime. What's it equal to? By assumption, it's equal to L, right? I'd like to find what is the length if we measure the rod in the other frame, right? Oof. I have this, my spider sense is tingling. I feel like I'm setting this up wrong. Ooh, we don't have enough time to fix it either. Rats. I'll have to come back to this next time. Let me do something that I can do in the time that remains. Sorry, I always get turned around in these two discussions. So it's my bad. I should have written these things out before I came to you guys here. So my apologies. It is nevertheless true that there is length contraction and time dilation. And this is observed, right? These things have been observed in the sense that, so for example, there are elementary particles that they're unstable, they radioactively decay, and various, you can do experiments to see how long they last. So there are particles that, if they're just sitting on a, just sitting in a laboratory frame, they'll last for, I don't know, like a microsecond, let's say, for the sake of discussion. And then if you can observe those particles going very, very fast, they might have a lifetime, not of a microsecond, but of like 20 microseconds. So this is that time dilation thing. Since they're basically moving clocks run slow. All right. And so I'll try to do some numbers next time with all that. But the one thing I can also talk about here is, well, how do velocities transform, right? So it's relatively simple. If you just kind of think about it this way, take the differential of this. So you have dx prime is gamma times dx minus v dt, and dt prime is gamma times dt plus v dx over c squared. If you divide these, you can discover the transformation law for velocities. So the gammas cancel, and you've got dx minus v dt divided by dt plus v dx over c squared. Now that's not terribly enlightening, but if you'll allow me to continue this formal nonsense, if we divide the top and the bottom by dt, what do you get? We get dx dt minus v divided by 1 plus v over c squared times dx dt. So if we say, you have a particle has velocity u equal to dx dt and u prime equal to dx prime dt prime, that would allow us to effectively compare the speed of a baseball in the fixed frame of reference, the unprimed frame, and the moving frame of reference. The velocities we'd be comparing would be the u and the u prime. This formula shows you what the relation is. What we have is that u prime is equal to u minus v over 1 plus uv over c squared. And so this is how velocities add. Not really, they don't add. This is how velocities transform in special relativity. So let's hypothetically, suppose you're on a train, right? And the train is going at the velocity speed of light over 2, right? And on top of that train, Mr. Top Hat, right, throws a ball at u, let's say u prime, right, equal to, c over 2. What's u equal to then? So by the way, this flips over. U is equal to u plus v over 1 plus uv over c squared, I believe. Minus, I think. Is it minus? One moment. A little fuzzy there. So if you plug in that, what do you get? Oh, come on. My notes are letting me down. I got all this other fancy stuff you don't care about. I don't care about it at the moment either. So I think there's a minus here because like that. Okay, so if I calculate then what's u? Well, I've got c over 2 plus c over 2, right? That is what we would. That's what we'd expect in Newtonian mechanics, right? If you throw a ball with speed c over 2 on a train going c over 2, your speed with respect to the inertial, the background frame is just c. Yes, sir.
Sorry.
Uh-oh.
Equation for u.
Mhm.
Shouldn't the u on the top be prime as well?
Yes. Thank you. Which I just made use of here, but yeah, thank you. Excellent. So and then we got what? 1 minus c over 2 times c over 2 over c squared, which is what? This is c divided by what? 3/4. Wait a minute. 3/4? All right, that's definitely a plus. So that gives me what? 1 plus 1/4 is what? 5/4? Yeah. So we get 4c over 5. So the way this rule works out is it conspires so that whenever you add velocities, you never get past c. If I go, if I throw a ball at half the speed of light on a train that's going half the speed of light, and then I ask you guys to measure how fast it is and you're off the train, you will measure 80% of the speed of light, not the speed of light. That's how this works. I mean, it's surprising, right? That is not our intuition, right? Your intuition is like velocities add, except when they're very fast, they don't. This happens. But anyway, I'm out of time.